Very nice to see you guys here. And this talk, I will have a lot of technical details. I hope this could be, helpful for you, or you learn something new. So currently, AI for healthcare. Anyone actually tried ChatGPT on any healthcare-related issues, and they provide a good answer? If yes, please raise your hand. Okay, several. Oh yeah, double hand. Okay, great. Yeah, we're actually living in the very interesting. Let me see how I can move. Yes. Okay, I have some disclosure I have to say, and let's move next. Okay, so yes, so we actually are living in a very interesting period right now. We are experiencing, people say, industrial revolution of 4.0. I will say the first revolution of intelligence. So AI can play a big role in many domains, including the healthcare. And this is a book by Eric Topol. If you want to read, it's called The Deep Medicine. It's a very good book, actually published before the pandemic. This is the wish he outlined, what AI can do in healthcare, including many things that you think is really impossible. Actually conquer the impossibles. Yes, I will not go through the details, but this is very outlandish expectations. How to reach these expectations? So first, there's a lot of things about people try to figure out how we apply AI in healthcare, and what's the relationship between the AI and doctors. And this is Kurt Langetos from Stanford AI Health director. He actually said, so all doctors will embrace AI. If radiologists don't replace AI, it will be replaced by radiologists, not by AI. By radiologists, they like to try AI. I think that's the way how they're going. So look at this, sorry. Try to figure out how to point it. Okay, yes, look at this curve. So human error average is 5%, okay? And the machine error started with 30% in 2010. Okay, you see this error rate is going dramatic down, especially passing 2015. Human make less error than, machine make less error than humans. So basically, you see, for human error, if we have 3 to 5%, for radiologists, there are 40 million diagnosis error happened every yearly, in the world, because we have so many medical imaging you can take, especially chest X-ray, okay? But machine can reduce this error dramatically. So this you already feel, that is our next step, is how we apply this AI in healthcare. And another thing is, healthcare is the wonderland for AI. Why? Because healthcare has lots of data. Since 2015, we have this iPhone, we have the sensor, we have the app. Lots of patients leave digital footprints in the digital world. So basically, you see the healthcare data compound annual growth is 36%. It's more than any other industry, including the retail, okay? And per capita, per day, digital interaction dramatically, you can see, is exponentially, even to 2025. Everybody will have around 5,000 interaction with your digital apps per day, okay? And lots of these relate to your food, your nutrition, your exercise, your conversation. Conversation is part of the mental meditation for your health, okay? And also COVID created the telemedicine. And even better, even your conversation with your doctor, all your everything is conduct through the internet. And this actually generate a lot of data. And of course, since 2015, all the hospitals and clinics are mandated to use EHR system, electronic health record system. And this is all digital records. They're actually about your medical claims, your mobile sensors, and your retail, non-retail outlet, and hospital stays, and everything will generate as a data. This data is actually high quality data. It's not like the book review or product review from Amazon. It is generated by doctors, curated by high professional certified expert. So also, the healthcare data is very rich. It's cross-modality. I tell you, we are fascinated about, ChatGPT. Anyone play DALL-E? DALL-E. So actually, text to image, right? You give the text, you generate art. So cross-modality is the big advantage for deep learning. Deep learning can deal with this, but normal machine learning, I will say XGBoost and all these other logic regression and linear regression, won't be able to deal with cross-modality data. And but in healthcare, we have lots of cross-modality data. So you can see, this is MR image, and this is check accessory. And for each image, they have radiology report. And we heard about a lot of computer vision look at, cool image detect the dogs and cat and also, but this image has no human annotated notes, because nobody take a picture about cat, they will write a big diary about how this picture being taken, what is it about. But in any medical imaging, the radiologist has to write a very professional notes, and this is a text file. Together, we can do a lot of amazing things. Furthermore, you have EHR, which is Tableau data, right? So talk about patient information, medication is in the Tableau. It's a structured database, right? Then you also have time sequence data for your vital sign. So your oxygen, your vital sign, your blood pressure is actually time sequence. First, last, you also have a wave data because the EEG, ECG, your heart, your brain generate a lot of electronic waves. These are captured. How can you mine all of this just in XGBoost or in machine learning? It's impossible. But I cannot move to next. Okay, too fast. The mouse, okay. Okay, great. So you as a single patient, you actually going through a lot of data points. You leave a lot of data points. So you go to you have to claim, go to hospital with the doctors and buy grocery food, and your life insurance company and your health insurance company, your payers, and all this, and even all these sense. From all your body, you can wear all different sense and capture your daily pulse. And all this data will generate a big data for healthcare. And I tell you, deep learning is the best solution because deep learning is the best way to deal with the cross-modality data. So what this means cross-modality data is for your Tableau data, for medication or your Tableau data, you can create them as embedding. Just use any in like neural network, you can get embeddings. And for this time sequence data, for your vital sign, because it's every second hours you have your vital sign measured, right? This you can use RNN to get embeddings. For your medical notes, which is natural language processing, you can use BERT, clinical BERT, all these transformer to get embeddings. For your image, you can use GN, you can use CNN, ResNet, and DenseNet to get your embeddings. And for all the other sources, you can always create embeddings. And once you create all these embeddings, you can concatenate them together, or you can fusion them together. There's multimodal fusion learning. And after this, you can do all these downstream tasks you actually are dealing with daily. Like prediction, linear model, you can put this as linear model, clustering, and XGBoost. But with this embedding as an input, you get better result, okay? And what is embedding? Anyone know what is embedding? Okay, great. Embedding is the language that the AI speaks. Like we speak English, we can communicate, right? AI speaks the embedding. AI speaks embedding. This embedding can be communicated across modality, across different data set. So what is embedding? Embedding is nothing about just these numbers with dimensions. So dog is the entity with the embedding all these numbers from -1 to 1. It's not a probability, it's just a number. Each dimension has no meaning, but you can infer some artificial meanings. But this is the vectors, okay? And you have a puppy, you have a cat, all these vectors. This is a machine captured through the context and your corpus. And they get this embedding. If you plot this embedding from 7 dimension into 2 dimension, you plot here, you suddenly have some semantic meanings because we know puppy and dog are very close and they actually are very close to each other. And cat is a little further, house is quite further, right? So you can see this semantics has been captured here. And furthermore, we can, because the vector can have, you can add vector together, you can minus vector together. If you add, like king, you add this vector together, you get a queen. So you can do some inferencing just by simple addition. So this is so amazing. And further away, so I have this check-access image. I just use simple encoder, get the embedding, right? Through the embedding, I just use the very simple decoder. I can generate reports. So it's cross-modality. Is give the image, I can automatically generate reports. The only things, because they speak the same language if embedding, they just change the embedding of image into the embedding of the words. Okay, same thing. You give me the medical notes, right, report. I can generate the image of this because I convert the text language into embedding, and from this embedding, I can convert that embedding into images. So after you have all this fantastic embedding, the cross-modality, you can actually plot them because embedding is the high dimension. You can just plot in 3 dimension or 2 dimension, which you get actually the clusters. So all these clusters, you can suddenly find, oh, this is a phenotype of patient. So for instance, this is a patient with a stroke. They actually cluster together. This is a patient with heart failure. So you can easily do this by using all these different data, like a cross-modality image, nodes, and the Tableau data together. You can suddenly do all this clustering and prediction. So just because of embedding, okay. Anyone heard about transformer? Transformer. Yes, great. Actually, ChatGPT is a kind of transformer. It's language transformer. And transformer start from language. So transformer is not, this is the typical model of transformer. Look very complicated, but actually it's just the embedding and encoding and decoding. So you first encode your input, then you decode your input for output. Okay. So this embedding, this bird, it's the first transformer from the NLP text part, and this is their series just adopt some self-attention. They can give attention a weight, so they can have weighted attention to generate a better result. And this is also already, say, the GPT-3 is using this kind of thing. And GPT-3 currently is powered ChatGPT, and GPT 3.5 will be released very soon, 2023, hopefully. And these things can be used for health risk prediction. For instance, you can predict end of life, very accurate, surprisingly. And we have local startup here. They actually, predict end of life and surgical procedures and hospitalizations probability and length of stay in ICU. So those are very important questions in healthcare. And the problem is the transformer is heavily dependent on what you train, right? So in healthcare, so most of the transformer is trained on Google Book and Wikipedia. But in healthcare, the terminology and things we talk about are quite different. So you have to retrain this on the healthcare-related things. For instance, PubMed article, we have 32 million PubMed articles, and we have a mimic data set, also a synthetic patient data set. You can use this together to train. There's a lot of different birds come out already, and you can use this to do any downstream task, what we talk about, like health risk prediction and so on. Transformer start from text, also get very popular now on vision. So vision transformer called VIT, it's actually patch your images into different patches, then had encoder, and consider the patch and position embedding, and generate the encoder, and use MLP to do any downstream task. Say, is this tumor or not tumor? And you can see this is a comparison of the, so this UNet is not transformer based. And this is the ground truth. These 3 is all transformer powered algorithm, which I think they have a much better result than the non-transformer powered vision transformer powered. You can see the result is really great. You see this, they have a tend to, with non-vision transformer powered, their areas tend to larger and can now narrow down to smaller area. With transformer, you can get a better focused area, okay. And also for the, this is, say, how vision transformer can be used in healthcare, like segmentation, organ segmentation, tumor identification, CHEK-SET3 diagnosis. There's a lot of area you can apply. And the thing is, when we have a lot of embeddings, how can we get them together? We can just concatenate them together. We can also fusion them together. So fusion algorithm is getting really popular right now. So basically, you have all these different embeddings. So you concatenate them together is the easiest thing, just add together, right? But you can have like 6 different, even 7 different fusion algorithms. So you basically, you don't concatenate them together. This is, you run another layer of neural network and get an embedding. Or you get the embedding, use one neural network to get those embedding and use another neural network because this is image. They use different neural network. And then you get embedding. After this, you get another neural network, get embedding. So for each modality, you use NN with neural network to get embedding and then cast them together. So there are all kinds of concatenators here. So you get all these things get embedding like this. This image, you get embedding like this, and then you just add them next to each other. We call it concatenation, and add them together, take average. So you have all kinds of different ways to do it. And this is the method has been applied to identify pulmonary embolism. It's actually achieved much better result. And anyone heard about knowledge graph? Okay. Knowledge graph is, I will say, even like ChatGPT and everything, like knowledge graph is the brain of AI. It's also, it's like our brain. The brain is connecting the neuron, right? We have a knowledge connected dot. So there's a lot of effort going on, actually could create a knowledge graph. So this is the drug discovery. In drug discovery, there are different data sets, talk about gene, drug, disease, and side effect. They are relational database. They are isolated. So if you want to know the drug connection with other genes, you might search all several different databases. So this is the effort we create to integrate all. So each box is a relational database about, it's a really large relational database about drug, gene, disease. You integrate these 20 different databases together into triples. Graph. Graph is just 2 nodes connected with edge, right? You can create a graph. After you create a graph, you can do a lot of graph GN, even heterogeneous graph transformer. Graph transformer also can be used in graph. You can use heterogeneous graph transformer to get the embedding of all these nodes. Suddenly, this is the drug repurposing. So each node is a drug. And nodes and nodes connection is because we created this knowledge graph. We calculate the embedding of each node. We calculate their cosine similarity. If the cosine similarity is higher enough, so they will have an edge connected. And this color is actually here is disease. You can see in this one, you have 2 colors, right? So a lot of color of drugs acts about insomnia. But this drug is treated by migraine, but it has high association with all these drugs with insomnia. So you can generate hypothesis. So whether this drug can be repurposed for insomnia. So those you can use this to generate hypothesis. A lot of pharmaceutical companies are heavily invest in knowledge graph to generate their hypothesis. And knowledge graph also goes on to the clinical side, like clinical trial. In clinical trial, this is a clinical trial knowledge graph. The clinicaltrials.gov has a lot of clinical trial data, but it's not very well organized. Their entity is not connected, not extracted. You can connect them together, and also like NIH has NCATs. They spent 20 plus years to build these ontologies, triples, knowledge graph, all connected with gene, tissues, and all these things. You can actually connect them together to get a better understanding of clinical trial. And because clinical trial is very expensive, everybody wants to save the money and shorten the length because it takes like 13 to 15 years to develop a new drug. The majority of the time is actually in clinical trial. So with this knowledge graph technology, you actually can go a little further. And plus, we have a PubMed knowledge. PubMed is 32 million articles published by, even not only researchers, also practitioners like you guys. So we use BioBERT to extract the bioentities from this abstract of titles and abstract of the articles about gene, drug, disease, and connect with the authors, their findings, their affiliations. So this is, you can see, we have a large number of authors, like 14 million, and the bioentities and those. With this, we can do key opinion leader identifications. So in key opinion leader, it's very important in pharmaceutical, also in clinical trial, they need to identify opinion leaders so they can promote their product or reach the patient recruitment. So we can see, we can figure out, using these things, we can see that Stefan is actually leader in the headache area. He published 450 papers and all cover this bioentity of the gene drug disease, and this is show his current activities. He might be active for certain genes for his previous career. Now he might change his focus in other genes, but you can see this pulse very actively. If you are interested in certain gene, you can see who are the published most paper in this gene and get cited. So this is key opinion leader. And you can actually combine this preclinical and clinical data together. So clinical trial is clinical data. PubMed and the drug and gene is preclinical data. If you connect them together, so connect with the preclinical about biomedical research and clinical data together, you can do a lot of interesting things. So this is a UCSF just published article in Nature. So they actually use their preclinical drug, genes, disease, and connect with clinical and actually to try to figure out the patient cohort for clinical trial, which is one of the very difficult questions to solve in pharmaceutical area. I want to highlight some of the research at UT in my group. So we actually focus on medical imaging and very important things. So for this CheckS3, you go to ResNet, you just use a little supervised deep learning. We use contrastive learning. Our contrast learning is human-centered. We want to incorporate doctors' knowledge into the deep learning to supervise deep learning to generate a better result. So we incorporate doctor knowledge as radiomics. So radiomics is the technology that doctor used before the deep learning even started. Okay, we put this as a contrastive supervised learning, and we just do the disease detection, which is 14 lung diseases. Okay, we can reach very high accuracy. Plus, we can show the explainability. We can show where is located. So for each image, we have to show the localization. And you can use the deep learning, use the integrate gradients to show the attention score, to show the localization. Furthermore, for medical notes, in the medical notes, this is a kind of medical notes. In the medical notes, the very difficult part is the relationship extraction. So you can easily extract gene or disease, drugs, medication, but it's very hard to extract the relationship. So we use the prompt-based. So through the prompting is the technology right now in the ChatGPT. So it depends on what kind of prompting and short and few short and zero short learning. You can actually extract with high accuracy, all these relationships from medical notes and their assertions. Okay, you can see the disease is present or current and maybe possibility. Those you can identify with high accuracy. And this is a disease progression model. So every disease has their own progression, right? And a different person has a different progression timeline because different person has the different prior conditions. So we use the temporal embedding, and to embed all these temporal models, return models, and together we can generate personalized disease progression model for each individual patient. So we collaborate with the largest health insurance company to do their care management. We can propose the personalized care management plan for their individual patient because we have this individualized disease progression model, yes. And explainable AI is also very important. There are all kinds of different methods. In the image part, you have a GrandCam. Anyway, so GrandCam, there are different kinds of GrandCam, and the major things in the GrandCam is they tend to identify much larger area. So how you can focus on the smaller area. So our method, we use the deconvolutional neural network. So all this CNN is convolutional neural network. You use deconvolutional neural network, you actually can identify much smaller area, much narrow area here. For the explainability, people use shape and line, right? Shape and line. But the shape and line is very expensive computationally. So we actually, together with Macomb Business School professor, we identify a method that you just combine the back-propagated intergradient gradient descent plus ablation study. We can generate a better and fast explainability for health risk prediction for length of stay in ICU. Just the last few slides is the ChatGPT. I cannot close my talk without talking about ChatGPT. Yes, so this is the medical notes. It's a de-identified medical notes. It's like a female falling in the bathtub and has a headache, and she sees some silver speck and dizziness. Those is very long. Sometimes it's very hard to understand. If you give to ChatGPT, you say, ChatGPT can do very good summary. So you can say, can you summarize this above medical notes to a layman person? And this is a pretty good summary. It's shortened and is talking about summarize what happens. I say, can you summarize this to a 5-year-old? So you can see the difference. This is actually, this second summarization actually has a certain flavor to tailor to 5-year-old, to kids, to understand these complex medical notes issues. And also, you know, in medical notes, they have a lot of coding. So you have code ICD-10, SNOMED. Those are ontology terms you have coded before you can send it to the hospital. So healthcare hire a lot of people manually code this SNOMED and ICD-9 code, 10 code, but actually GPT can do this. So I say, can you extract SNOMED CT for me from these notes? And first, he said, from above notes. Okay, he said, oh, sorry, I cannot extract SNOMED CT, but I say, because there's no SNOMED CT in the notes, but I say, headache is a SNOMED CT code term. And he said, yes, headache is a SNOMED, and he gave me the headache, even the number, the coded number of the headache, and explained to me a headache. So ChatGPT did have potential, actually can annotate the medical notes, which a lot of companies make money using their NLP, but ChatGPT might be able to generate a very different solutions and fast and easy solutions. So these are the landscape about AI in healthcare. You can see it's a patient facing all these AI chatbots talking directly to the patient. And we have a telehealth. We have a doctor facing. So doctor also use medical records and these things to help reduce their burnout, right? And we also have drug discovery for pharmaceutical company and clinical trial. The challenge is there's lots of missing data and how we deal with missing data. So you can see the black part is all missing data. How do you deal with using variational autoencoder or GAN model, or even very cool diffusion model, because DALA-E is diffusion model. Or, you know, there is, because data cannot be shared. We're using federated learning. So a lot of federated learning actually going on to solve the problem. The data cannot be shared across different hospitals. Finally, I want to announce another event. Actually, here happened right now, not right now. In this year in Austin, in May 1st, actually April 30 and May 4th, we have the web conference. Is very top. It's a computer science conference with lots of AI experts, and we have a health day. We have a health day, and we also have a knowledge graph day in May 1st and April 30th. So it's actually on campus of UT Austin. Okay. So those are my collaborators. I'm happy to take questions. Oh, okay.
Hi, can you hear?
Yeah, it works.
Hello. Okay, great. Thank you so much for the talk. I had two very small questions. Firstly, I was very interested in your work with the joint learning and multimodal learning. And you mentioned several fusion strategies. Is there a particular fusion strategy that has worked well for you? Also, in case if you've tried like something like a single architecturally like cross attention, has that also worked better than fusion? Just to get an understanding of what you guys have tried.
The fusion learning has all these different strategy. I tell you, different question has a different way. There's no one fusion strategy works well for all problems. So for our problem, we currently try to look at ICU length of stay prediction. So we test all these six. It's here, right? All these seven strategies. Actually, I think it's early fusion is better for us. The early fusion, and especially joint full fusion. The first two works better for us for the ICU length of stay. We don't have image data. We only have medical tableau data, demographic information, medication, lab result, and medical notes. So basically they're all text data. Yes.
I see. So it's single modality, but different.
But I will say cross-modality because it's the tableau data plus text data.
Got it.
Yes.
Got it. And then the second subpart was you mentioned a lot about the prompt engineering research that you guys do, and there was dependency parsing, which is some concept is connected to another. When you said prompt engineering, did you guys train that dependency graph, or were you able to use existing models like BioBERT and do zero-shot learning on top of that?
We try to do the chain of thoughts. Have you heard about chain of thoughts?
Yes.
Yeah. So we try to use prompt to build the chain of thoughts of the inferencing sequence to let the large language model LLM to generate chain of thoughts things. Use different prompting. There's a different prompting technology, right? Yes. You have simple prompting. You have other prompting. There's other slides. I couldn't put it here because yes. I'm happy to chat more afterwards. Yes.
Yeah, sounds good. Thank you so much.
Thanks for the
Awesome.
questions.
Thank you so much, Ying.
Okay.
Give her a round of applause.
Thank you.